All right, yeah, thanks, Jack. My name's Aidan. I'm finishing up a PhD student over here at Sheffield, and I thought I'd just take the opportunity to give a run through of some of the a couple of the key zones I've been looking at during my PhD. So broadly focused on, ceramic waste form and process development for plutonium disposition. So once again, looking at some slightly unique waste, but at our challenging site as opposed to the US's challenging site. I'll give a brief introduction to this. Are we using this for film, or is this just for the online stuff? Cool. I'll forget that. So the UK currently holds around 140 tonnes of civilly generated separated plutonium in secure storage up at Sellafield as a result of many years of reprocessing operations of spent nuclear fuel. Following several years of underpinning research, the UK changed its government policy in January of 2025. So now we're going to move towards, at least in the interim period, moving towards processing all of this material for final disposition in GDF. And so option development has already been going on for this to develop basically full ceramic materials capable of immobilising plutonium, and this is the subject of a lot of our work. Now, in terms of requirements for these materials that would need to immobilise plutonium in GDF at the very centre of a multi-barrier system, there's really two front runners that are under consideration at the moment in the UK. The first of those is referred to as disposal MOX, which is essentially a fluoride structured ceramic based on the structure of mixed oxide uranium plutonium dioxide fuel, but with some neutron absorber added in to prevent criticality in canister. And this, by sections of the industry, is seen as quite attractive, given that it's a material that we know can incorporate plutonium to fairly good waste loadings at atomic scale. It's highly radiation resistant in terms of its crystallinity, and also really the main advantage to this is it's seen as having a fairly safe and reliable production process. Given that mixed oxide fuels have been produced at scale in the past, it's seen that it wouldn't take big adaptation to the process to be able to produce enough of this material to immobilise the entire of the 140 tonnes that would need to be disposed of. However, the other material under consideration is that of zirconolite ceramics. And these have been widely investigated in the past and have been shown to be able to incorporate plutonium at atomic scale, although there is more complexity about the different phase fields that can form. But really the big question mark that we seek to answer in this work is that bottom point of a safe and reliable production process, because nobody's produced these materials at scale before, so understanding the kind of parameters on the flow sheet that would need to be underpinned to be able to produce these materials at scale is the focus of a lot of research here.
Press escape and try.
Yeah, I will do. Let's go off. Okay, alright, there might be some carryover issues from my version, but that's okay. Our points just have an absolute freak out here.
It's waiting for a change in government policy.
Yeah, mine.
You're waiting a while.
Yeah, computer's just frozen.
Right, okay. Control delete stuff.
Yeah.
If you plug in your memory stick that you used to transfer it on, if you've got it.
My laptop's up there with the presentation on it. I can put it directly to that.
I'm just thinking for the online bit. If you've got from the USB.
I think Ferguson got from me.
Oh right, okay, that's fine.
Yeah.
Do you want me to bring your laptop down?
Yeah, grab that. Unless it's, yeah, okay. I don't know. Yeah, I don't know what's on there. Half my slides were to me, so I don't know what's on there. Cheers. Sorry, thanks.
Yeah. She's done it already.
How do we change the input from?
On the little screen, data.
So,
It'll go data. It'll go HDMI.
She gave me a quick. It's.
If you hit dual
Sensor
at the bottom and then select HDMI.
The miners
Well,
on.
that's what I was to do
Yeah.
for easy scan, so we can
Yeah.
fully
Press the power button on the PC monitor as well, just to turn it off, because it'll turn the left screen off.
A really big delivery.
There's a big power button at the bottom of the screen.
What I usually get, and he's offered me 2 bags. Well, I've got 100 kilos, so that should keep me going for a while anyway. But I just get a bit panicky when I get lower than 2 bags. Yeah.
Panicky when we get less than 5 kilos.
Oh, the HDMI port on this laptop.
But I have to make sure that
Sorry, yeah, I've
stop
got the USB
coming
stick,
around
yeah.
and helping themselves to that.
Sorry, yeah, my bad, I forgot about that. Yeah, yeah.
Or cleaning.
I've got an adapter for it, but it's at home, so I don't know.
Cleaning person more.
I can present it straight off the USB stick here. Yeah. But I don't know if it was like, I don't know if PowerPoint on this.
We've got some that we bought from for filling up sandpit. That's silica. I'm considering getting that analysed as well, see if it'll work.
Yeah, sorry, I can
But the one that we've had is the super pure, crystal glass stuff.
Great. Most of the time it's completely
Yeah,
unnecessary.
I just need to find out from Russell what he wants to do. But yeah, it looked like a reasonable.
I can't
Can't
confirm is
is
how
very
varies
big.
over time. You know, if you order it now,
Yeah.
6 months later,
Because I'm seeing, yeah, because it depends on who they buy it from, and because all they're doing is counting.
You just turn off the PC screen again.
Yeah.
But no, when
So you're right, we'll go off one side.
that's what services just said, oh no, we're stopping carrying that unless you want half a ton. It's like, yeah, that will take me over 10 years to get through.
Right, at least for now, we're on one stream. Alright, yeah, sorry about that. PowerPoint just stopped working on that computer. Alright, so I'll restart my flow. So, essentially, up until now, there's 2 main ceramic candidate waste forms, and we're focused on zirconite, a CaZrTi207 ceramic. And realistically, one of the main barriers to implementing this is understanding how we can produce enough of this material at scale of suitable quality to be able to cope with the amount of material that we need to process into a waste form. Now, in terms of where we get the idea of zirconite from, this goes right back to the cool guys back in the 70s and 80s that were looking at Simrock waste forms. So originally these were multi-phase ceramic waste forms based on mineralogical understanding of rocks and minerals that could contain actinides for very, very long periods of time. And they designed multi-phase ceramic waste forms to cope with all of the hazardous elements from reprocessed spent fuel. But zirconite was seen as one of the main actinide-containing phases here, and given that now we're looking at a separated PuO2 waste stream, we can look to target single-phase ceramic waste forms to simplify the procedure somewhat. So CaZrTi207 has this layered monoclinic structure in its prototypical form, and it's been shown that we can substitute plutonium onto both the calcium and zirconium sites in that structure, alongside a suitable charge-modifying additive on the titanium site to maintain charge neutrality in the structure. Now, a lot of work's been done on compositional development of these in previous, and so for the rest of this talk I'll focus on material of a particular composition that's been underpinned as the sort of UK baseline composition for now, for what would be a zirconite waste form. It's not exactly this composition below, but essentially this involves doping uranium as a plutonium surrogate into this material using iron as a charge compensating compound. Now, in terms of what the status quo is of this material at this point in time in our understanding, a lot of it is based on very laboratory scale processing techniques for ceramic manufacturing. So a very standard solid state process of milling together the components listed on the left hand side, cold press and sintering to make these ceramic pellets. And this has been nicely developed for the compositions that we've spoken about, to be able to make nice single phase materials to look at underpinning leaching behaviour and these kinds of experiments and radiation damage behaviour as well. So this is what's been done in terms of the material development, but actually in terms of implementation of this and the scale up that I've been speaking about, there's some major issues that we look to try and address. Those being essentially the longer dwell times that take place in this pelletization process to be able to form these quite refractory materials, and also during the powder processing, this extensive planetary milling with a carrier fluid is seen as quite unattractive to be able to scale to real plutonium material, because you'd have a large production of secondary waste stream and it's something that would be preferable to avoid. So there's two real areas we can look at to target for how to process these. The first that copes with the sort of scalability of these small pellets being able to make bigger pieces of material is hot isostatic pressing, and this allows us to make much larger work pieces and essentially have a batch through process to be able to produce this material with much shorter dwell. And what this essentially means is we take, instead of just uniaxially pressing individual pellets, we take our powders and we put them inside a stainless steel hip can, weld it shut and evacuate it, and then put it in our hot isostatic press. So essentially this is a small furnace inside of a pressure vessel. So you have simultaneous application of high temperature and also high isostatic pressure. And this can drop your dwell times down to about 2 to 4 hours as opposed to 20 to 40 hours on conventional sintering. And this is also something that's used in a lot of other areas of metal and ceramic processing. It's seen as quite scalable. So we think of this as a little bit more scale independent than cold press and sintering. So you can scale this quite nicely to much larger pieces than this. So you make quite small hip samples, but the thinking is you could make much larger work pieces without too much difference to the process. However, there's a difference here in that this is done inside an evacuated canister, so the chemistry inside that canister is going to be different to what you would observe inside a standard furnace. So looking at essentially step one here is we've got this nicely optimized material that we've produced with our lab scale cold press and sintering process. Can we essentially make the same material with HIP to then give a good benchmark and baseline to then look at further process development beyond that? And yeah, just another run through of when we hit uranium materials here, it adds a few extra steps which I won't go into, yeah, this is linking to what Lewis was talking about earlier about our sort of quite fairly unique capability of being able to make these samples. So I'll basically speak about these two areas separately. First of all, this HIP validation, and then I'll look at some additives that we looked in afterwards to try and target some reduction of this high energy milling. And then I won't speak about this today, but I've also worked on some different powder processing routes using a wet chemical route for higher reactivity feeds, but that's not included in the presentation today, just in case you were sitting there wondering why hasn't he used wet chemical routes. I have, but not in this work. So if we go back to our most basic HIP validation, first of all we can see that we can form nice zirconolite structures using HIP, but we do see some differences, and especially we can pick this out through rebuild refinement as some slight polytypism difference. So zirconolite has a few different stacking sequences that can form that broadly fall under zirconolite structures, and we find that HIP is more likely to produce a 3T polytype. This isn't seen as something that really significantly impacts the performance of the wasteform. It's just an interesting point to note that basically we can produce zirconolites with little evidence of secondary phase using HIP. So this was a good news story to begin with. If we look at this under the SEM, we can see a fairly consistent microstructure and fairly consistent incorporation of our uranium. Comparable density as well to our cold press and sintered samples, but as I say, achieved in this was a 2-hour dwell as opposed to a 48-hour dwell in a conventional furnace. The next step that we looked at to really underpin that we could produce this same, a little aside. One of the other complexities when you HIP, obviously we have contact with the stainless steel canister at the outside, so understanding this interfacial zone and essentially making sure that we don't form any uranium-containing phases that are less durable than our zirconolite matrix. We do form some secondary phase at this canister. You can see the chromium oxide that you would expect to be on the surface of the stainless steel canister, and then some interaction with the iron. This is believed to be a result of diffusion of iron into the ceramic as well as the iron that's in the ceramic already. And you can see what we believe are some pseudo-brookite phases that form near the phase boundaries. But these we believe to not incorporate any uranium, but we are looking at some more in-depth study to confirm that using EPMA. But essentially, these interfacial regions are not thought to be particularly problematic. The main difference we do see is the difference in grain structure, and this will be the subject of some further work, especially that Alex will do on the impact of this grain size on some of the radiation tolerance characteristics of these materials. But certainly that's one of the main microstructural differences that we see with HIP. We also, if we stitch together some longer images, we see we get fairly consistent phase formation across the centre of the canister. It's only really this very small interfacial region that's affected by the metal contact, and the rest of our ceramic is formed quite nicely. Now, what we look at next is essentially a little bit more in depth on the uranium to ensure that it's formed that it's got the same speciation that we want it to have. And understanding what the uranium speciation is in these ceramics is useful to link to the dissolution data. So first of all, we did some HERF-D spectroscopy on the cold pressed and sintered sample to understand how uranium sits in this structure. We see a mixed U4-5 speciation, which we don't have the equivalent measurement on the HIP materials just yet, but this is essentially a good baseline to understand that we have majority uranium-4 plus retained with a small amount of oxidation to uranium-5. And the comparison that we do have at the uranium L3 edge, measured at diamond light source, is that we don't see any strong difference in the L3 edge position on the basis of processing environment. And so what we can infer from that is that essentially, when we do measure the HERF-D, we wouldn't expect it to look much different. So the uranium oxidation state looks to be fairly unimpacted within our uncertainty ranges here, which is good news. And if we extend that further to fit in the extended fine structure regions in the cold pressed and sintered sample, we can build quite a nice model of uranium sitting on the sites that we think it is. And if we extend this model to the HIP material, it fits in essentially the same way. So there's no measurable impact on the uranium oxygen environment coordination on the basis of process environment here. So essentially, that first package of work underpins that we can produce this material in the same way using this slightly different processing method. Now, we already knew that heptaconolites were very feasible, but with this particular composition, this was a useful starting point to say, yes, we can produce this material. But I'll return now to what I said at the beginning, and really what we're interested in is trying to account for this difference in powder processing. And so we did that through the use of a copper oxide additive, which I'll talk about for the rest of this. Now, the reason we've used that in a typical solid state sintering process, it's purely diffusion controlled at surface contact between particle boundaries. And you've got two processes happening here. You've got interdiffusion of species to form the zirconolite phase from the individual precursors, and you've also got the densification happening at the same time. Now, in a purely solid state process, as I say, this is diffusion limited, and we end up with some retained porosity at the end, as we've seen already. So if you looked at other areas of ceramic processing, they might look to induce some liquid phase sintering as a method of being able to improve both the phase formation and the densification. And we see in literature that there's this eutectic interaction between copper oxide and titanium oxide that begins at around about 1,000 degrees, which it seems like we could make use of in these systems given that they're quite titanium rich and that TiO2 is one of our starting precursors anyway. So what we did initially was, essentially nobody's looked at this in zirconolite systems before, so we looked at just an undoped zirconolite first, and then we built that into the actual more complex simulant waveform compositions. And what we saw is that at 1,000 degrees on this left-hand side, with no additive, you see basically what you would expect if you just knock 300 degrees off your normal synthesis temperature. You've just got a load of retained precursor phases and not very much of what you want. But if you add in just 2% of copper oxide, you suddenly massively increase the amount of zirconolite phase that you've formed, and you just retain a small amount of secondary phase, even as low as 1,000 degrees, which is very, very low temperature. When you get up to 1,300, closer to the normal synthesis temperatures of between 1,300 and 1,400, you do retain some copper-rich secondary phases at grain boundaries, but this was basically our start point to say, okay, we can see a good interaction here. We can see a massive increase in the amount of zirconolite phase that forms, especially at low temperature. So we're clearly seeing some advantageous effects of this additive, and our density is higher with the copper oxide additive across the temperature series. This is all in cold press and sintered, by the way. I've not introduced any here. And so, again, we see these two different mechanisms of phase formation and densification happening at slightly different times. And so, after this, we extended this to the full uranium-doped baseline composition. So to start with, we just did a crystallization study on the undoped compound. You effectively just see at 1,000, you don't do a great job of forming the phases that you want, and you end up with some secondary phase in there. And you actually see this Schrankite structured phase in the interval of 1,100 to 1,300 that basically we think is just the way that this phase forms. That's eliminated by the time we get to our normal process temperatures of 1,350. I'll skip over that. So with the copper oxide additive here, we see that our proportion of zirconolite phase is higher across the temperature range, and we reach a full single phase at a little bit lower temperature. Now, lowering the temperature is not necessarily our main objective here, but what this is demonstrating is that we're improving the kinetics of our phase formation to be able to form a higher proportion of that phase at lower temperatures. And so, I'll skip over some of this in the interest of time. And effectively, you can see this real clear comparison at 1200 degrees of how much of an increase in density you get by adding this copper oxide. So really, the takeaway of this is 2% copper oxide is by far enough to make a significant difference on our sintering behaviour. And therefore, what we then try to leverage is can we use that to improve our phase formation kinetics to then be able to go back a step and say, if we can't do our powder processing as efficiently as we wish when we've got this higher activity additive to put in to make it plutonium active, can we basically use this liquid phase mechanism to allow us to form more phase when you've got a poorly milled product? And so that is what we then looked at after this. So we first of all took all of the inactive components and did our normal planetary milling procedure on these, which would be completely feasible at a higher scale to be able to do this process with the inactive portion. And then we basically add our UO2 in a very gentle mixing way. So this would be an ideal scenario to be able to have your kind of pre-mixed inactive feed that's kind of then gently dry mixed with your active feed in a much more low energy process that's going to produce a much lower hazard. And essentially tumble that together and then hit those with and without the copper oxide additive. So I did a little sample matrix here, but I'll just present the ones that were tumbled for the longest. It's worth pointing out here, you're going to have, essentially what we're doing is breaking the rules of conventional ceramic processing, because you would never want to have a poorly mixed, one of your components to be poorly mixed in with very little particle size reduction and very poor kind of particle contact. But we're seeing how much copper oxide can allow us to step around that and still produce something decent. Now, what we really see is there's free UO2 retained in all the compositions that we measured, but to varying amounts. And if we really look at this in detail, what you see here, with no copper oxide additive, you essentially see these big retained areas of UO2, and you kind of see these reaction rims. I don't know how well this shows up in phase contrast on the screen, but you can see close to these UO2 particles, you see the rim around that has got uranium incorporated fairly well into a zirconolite matrix. But if you move further away from these UO2 particles, you can basically see that there's no uranium that's reached further out here. And in the EDX here, you basically see no uranium incorporated into the zirconolite far away from your UO2 that's retained. By contrast, when you add a little bit of copper oxide, you get completely consistent phase contrast in your bulk with a very small proportion of free UO2. And so you have uranium nicely incorporated into your bulk zirconolite phase. This demonstrates this really clearly. So effectively, these have been processed with the same powder processing method, but just with the difference of additive. And you can see you're massively decreasing the amount of free UO2 and also massively increasing the consistency of the zirconolite that you're producing. So again, there's a clear impact here of copper oxide addition in such a poor kind of mixing method. So really, we're looking at methods to underpin the upscaling of these materials and understanding what steps we can take to kind of help to take these materials active at large scales. So yeah, that's some of the stuff that we've been looking at and demonstrated some preliminary success.
Thank you very much, Aidan. Do we have any questions?
Thanks for a great presentation, Aidan. I'm just thinking out loud here, but have you considered kind of like a cocktail approach in that your copper and your titanium are having low temperature liquid phase formation? Could you do the equivalent with the zirconia and come at it from both ends as well?
As in find an additive that
another additive that would preferentially form a liquid with the zirconia as well.
That would be super interesting. We've not extended it that far really because we've just been underpinning this particular interaction. But I'm not super aware of what additives do make liquids of zirconia. I'm sure I could look at
Hit the phase diagrams.
But yeah.
That'd be something.
Yeah, it'd be super interesting to look at. I think, first of all, we just wanted to demonstrate the impact of this in particular, and then, you could definitely add other stuff. I mean, Sellafield Limited, I imagine, will be interested to look at lots of different ways to make this happen. I mean, when you've got kilogram scale hip workpieces, they're particularly concerned with consistency across that workpiece, and especially in the centre line, tends to be quite unreactive compared to the bits further outside. So different forms of additive to increase the liquid phase definitely useful. Yeah.
Really nice. Thank you.
Okay, slightly cheeky question. How easy would it be to recover the plutonium if they change their mind?
Very difficult. I mean, deliberately, there's a few different ways that the policy gets framed, and realistically, the kind of phrase of putting the plutonium beyond reach is what we would aim for, especially in terms of things like proliferation resistance. So once you process these into these waste forms, the idea is you would never be able to easily recover it, and you wouldn't want that to be the case, because if you could easily recover it from a waste form, it's not a very good waste form. So it's kind of the final decision to be made on this. Once that's made, there's no going back. But this won't start to be implemented for probably a decade or more. It's kind of just underpinning what we can do with it when that decision has to be made. But like I say, policy has fully changed now that it will get disposed of as a waste. Clearly, there's a lot of people that would still view it as a resource that could be used to make new fuel, but that decision's been taken above my head, certainly. And I wouldn't want to design a waste form that would allow the plutonium to be easily recovered.
Well, let's thank Aidan again. While we address some technical issues, quick 5-minute comfort break if anyone wants to get more tea or biscuits or whatever.
Oh, you mean in terms of rates?
Yeah.
Combination I think the phrase is but I wanted to make it in because it's always good to hear some different interesting sounds from different places. I think I'm supposed to be talking as well. I think Lewis did this. Don't worry, because there was. Lewis did some slides at the start on capability. Oh right, okay. Lewis did that. So. Oh okay, I'll go and check with him. But yeah.
Yeah.
Do you not want to? You were last. So you think you don't want to? It's fine. I'm happy either way. I mean, I guess. You're supposed to finish it.
I realised, oh my god, I'm so glad they decided to
See if you've got time. I'd like to.
Yeah, so
they definitely won't be time for 2 hours. I've just been down for sort of 30 minutes.
It's much rent-free, doesn't it? Oh, I assume you saw the tattoo, yeah? You saw it, yeah? Is it only time I've ever looked at tattoo? Has it become a load of drops? I do recommend it. Yes.
Yeah, we take the full acting position.
Like, I only have to say, oh, I have
Hello.
No, no, as in you who's going first?
Neil did mention something about it was contingent on a forklift arriving.
So, forklift arrived yesterday.
Yeah.
Says in
The forklift.
into the loading bay to actually go
So if we do
Oh, he's messaging you guys.
yeah, so I can't get that in. The MCPs were supposed to be delivered on Thursday, but then they called and said can't deliver those because I've got access to hire, which is fine because we didn't have a forklift. Forklift came later than it was supposed to come anyway, and then we found out it was.
That kind of got you off the hook a little bit in terms of there was anything there.
So, well, we've got people from the team coming in next week to do some work. But they can't fully alert because we haven't got any MCPs. So anyway, they're trying to get a smaller forklift that still can lift 1.5 tons, small enough to fit under the ceiling. And I think they MC, yeah, I know. Yeah, I know they exist, but Eric looks like so that was fun. So yeah, that was going. What?
You know when you run out
What?
You know when you run out of funds on your booking account, you stop something out.
What? And I opened something.
Yeah, well, he's already said.
Allows for it.
You would have been a good first class now.
Yeah, I was asking to do it.
I managed to. I fudged things.
Yeah, see?
Find money where there is no money.
Yeah, I've got pretend.
I think Jack took him, yeah.
Just feels like a job.
So anyway, I'm really sure when they replace it.
You've got 3 seconds.
Because you've got very two one that can't get any.
New cryptocurrency just dropped.
TQs may or may not take next Thursday. And the bean.
They're going to sit around and talk about things.
Always I don't know. Whether that or something like changing
I can't get to pay, it's so deemed up. I can't actually take the bottom of the laptop off. So I'm doing this to keep it on my
Changing pressure. On the couplings. Right, okay.
I've got a fan train going from the other side. It's cool.
So, well, it's always difficult. Yes, so I mean, that wasn't it. That was one good thing that's come out of that. Is that
we did get a lot of the stuff cleared out of the evidence.
you should probably.
Some of it is actually moved to the lab. So,
You should.
left over 3 days.
I Apologise on his behalf. I guess it's always tough when you're trying to logistically trying to deal with a number of different moving meals.
They're expecting George Elkin to do the driving and stuff.
Has he? Oh, actually, I assume he's got a license.
They haven't done, until this day morning, they haven't got his assessments or anything like that. It's SOP for a week. Yeah, no risk assessment.
Well,
and he said, was only asked about trains last week. No.
Well, there's a few lessons. They're all meeting with
Yeah, I saw it earlier on.
A rod definitely thing.
Middle to long range communication required to.
I only hear about it.
Honestly,
Milo said, I've definitely spoken to you about it.
There used to be one
The MCPs, yeah, and then they decided to go get rid of because they thought they could do everything without the MCPs.
Oh, just off.
And it was costing so Ross decided they were going to bin that. And then obviously whatever stuff
That's the thing, yeah.
I think they're probably quite keen to actually do something on
he loves it. When we did new hymns on
see whether or not we could do it with
literally the entire drive.
civil one,
Do you know what? I'll walk with you. I'll follow you whilst you
200 kilograms.
also
I mean, I'm sure that they'll engineer it. If it's you'd be on a sticky liquid if something went snap.
just at that.
Or maybe 1.5.
Nobody even thought about these.
Because I suppose you don't. It's not like it needs to go very high. It needs to go.
We need to get it off the ground, take it through the lab. We tried doing it with when they first got them on site. We were doing it with pallet trucks in CD2 gauges, and you had to support it on. Well, because it has a pallet truck can't get in the same as forklift, so you actually have to build some supports for it to stand on. Putting those down would be interesting as well. Because a forklift you can drive in.
Yeah, we're going to
right,
we can all settle down again.
I'm going to bow out this one so I don't.